Hi everyone, I'm Kev. I'm a final year PhD student at the University of Leeds. Thank you for having me give this talk. So today I'll be talking about my PhD research, which is on continental rifting, the breakup of strong continents to form new oceans, and it's a process which evolves both temporally and spatially. However, overall it remains quite poorly understood and therefore a subject of significant ongoing research. In particular, we want to know more about the role magmatism plays in rifting, as magmas thermomechanically weaken the crust and hence promotes continental breakup by lowering the yield stress of crust. And a good place to see this all in action is the East African Rift, where East Africa is tearing away from the rest of Africa. From south to north, the rift matures, with the locus of extension deformation and volcanism moving from the rift flanks in the Kenyan Rift and further south to the rift axes in the northernmost parts of the rift and also the Red Sea Rift. My focus is on Ethiopia, an in-between stage showing the final moments of continental breakup, in which magmatism and deformation is focused in the rift centre like a mid-ocean ridge, but it's not quite there yet owing to a still thick lithosphere. Understanding the magmatic character of the Main Ethiopian Rift allows for a stronger understanding of advanced rift development, with implications for understanding plate tectonics and therefore things that depend on plate tectonics like the deep carbon cycle. We therefore want to know more about where and how melts are stored in the rifting crust, owing to this magmatic thermal effect on crustal rheology during breakup. The samples for this study are collected from the Boku Volcanic Complex, which is a quaternary caldera complex located between the volcanic centres of Gedemsa and Boset Barisha in the Main Ethiopian Rift. And the reason we choose this locality is just because of the purple shown here on the simplified geological map. There's a lot of post-caldera basaltic activity in the form of scoria cones and fissure basalts, which are linked to intra-rift faulting characteristic of the late-stage continental rifting I mentioned before. Here's a photo of our field team throwing a frisbee around within a scoria cone in the Boku Volcanic Complex. It's quite heavily quarried, as scoria is used locally as a road building material, but that provides us really good access into the interior of the cone where we can obtain fresh scoria. And from the scoria we pick olivine crystals hosting melt inclusions. Olivine is one of the first minerals to crystallize from mantle-derived magmas, and silicate melt inclusions in olivine are small parcels of earlier magmas that provide details of what lavas are before they're erupted. And they're these brown things over here. You can see them quite clearly in the zoomed in picture on the right. Melt inclusions also ensnare volatiles like carbon and water, at concentrations not observed in eruptive and degassed lavas. So what we've done is we've determined the major, trace and volatile element compositions of the melt inclusion glass, but today I'll focus more on the traces and volatiles. And new to the Main Ethiopian Rift is the use of Raman spectroscopy to assess the density of CO2 within melt inclusion shrinkage bubbles, which, as you can see from these small circles present within those brown melt inclusions, are quite common in Main Ethiopian Rift melt inclusions. This allows us to combine the CO2 in the bubble and a melt inclusion glass to determine the overall CO2 within the melt inclusion. And here we consider some trace elements of our melt inclusions. Here the coloured circles mark my samples, with the colour dependent on the amount of melt inclusion post-entrapment crystallisation that has been corrected for. The black squares are olivine-hosted melt inclusions from other Main Ethiopian Rift localities. Those are from Fiona Idden's work, and the blue crosses are Main Ethiopian Rift basalt whole rock data. The lines shown here are rhyolite melt fractionation curves, modelled for trace elements through Rayleigh fractionation from our three most primitive melt inclusions. And what we see here is that the melt inclusions are, in general, less homogenized than the whole rock data, which is somewhat to be expected. And we can explain most of the scatter in the melt inclusion data, either through mixing between more and less evolved melts from a single parental melt during storage, or through heterogeneity of the parental melts themselves. So it's in these two ways that we're able to explain the scatter into trace elements. However, we can't account for scatter and rare earth element ratios using the mixing of more and less evolved melts. Ratios, unlike absolute concentrations, are mostly unaffected by fractionation, which is why the fractionation trends in the ratios look so flat. So in order to produce this scatter, we must therefore have a degree of parental melt heterogeneity, which is only mixed prior to eruption to produce the homogeneous ratios observed in whole rocks. And to preserve this heterogeneity in the crust, we must have environments of olivine crystallization that are kept separate prior to final melt homogenization and eruption. So what we believe this demonstrates is the existence of a network of stacked sills within the crust, each with their own distinct melt composition and each with their own olivine crystallizing. And we can also use trace elements in conjunction with volatile concentrations to describe the degassing of magmas during ascent before they arrive at these sills. Here we use ratios of CO2 with barium and rubidium, two elements that have similar mantle melting partitioning behaviour as CO2. My samples are now divided into two here. Those of which melt inclusions are known to have total CO2, so that's bubble and glass, those are shown as the blue circles, whereas those for which only minimum CO2 is known from the glass are shown as the red squares. And what we observe is from these plots, and I'll get my laser pointer out for this, is that from an initial concentration, possibly similar to that of undergassed mid-ocean ridge basalt. There is a first stage of degassing linked to ascent from the mantle or deep crust. This is then followed by a period of melt storage, during which the trace element concentration increases as fractionation progresses, before a final degassing stage then accompanies ascent during eruption, and that's this tail over here. We can also use volatile concentrations in concert with volatile saturation models to determine pressures of storage in the rift crust. Through the use of the Python library VSiCal, which Penny and Simon will give a workshop on during this conference, we can rapidly assess saturation pressures of volatiles within silicate melts. Here we use the MagmaSat model, which, when compared to other basalt saturation models, provides a difference of about plus or minus 300 bars or about a kilometre, so the uncertainty is not too significant. The figure shows that the major control on determining saturation pressures is CO2 in my melt inclusions, and it's also worth pointing out that water in undergas samples lies between 1 and 1.2 weight%, suggesting that this is a primary value of water. Here I plot saturation pressures against magnesium number, a measure of iron-magnesium ratio in basalts. The squares are again olivine-hosted melt inclusions of Iden and Edmonds, with pressures also calculated now using VSiCal. Here we see that the majority of data, both from my part of the rift and elsewhere, plot above 15 kilometers depth, and those for which total CO2 is known plot in a very narrow band between 10 and 15 kilometers. And that suggests that melts underneath the Boku volcanic complex are focused within this very specific, very narrow depth range in the mid-crust. And such a view is already mostly supported by geophysical studies, which suggest, for example, from magnetotelluric surveys on the left-hand side and seismic tomography on the right-hand side, that there are these high conductivity, high P-wave regions present at mid-crustal depths under the Ethiopian Rift, which can now be supported by my own petrological observations as being stacked sills. So finally, I'm going to end on more recent work by Emma Chambers, who has identified major seismic radial horizontal anisotropy at 5 to 15 kilometers in the main Ethiopian Rift and surrounding areas, which is less prevalent both at depths greater than 15 kilometers, i.e. the lower crust, and also at Afar, where oceanic spreading is incipient. In other words, sill formation at mid-crustal pressures at around 15 kilometers appears to be the dominant storage mechanism in the main Ethiopian Rift, and understanding how these sills form and the role they play in dictating final continental breakup must be a subject of future research. So we are now starting to assemble a picture of what the rift crust looks like from geophysics and my petrological observations. We know from volatile saturation pressures that melts are likely to be intruded and fractionate in a narrow depth range under the Boku volcanic complex and possibly other parts of the main Ethiopian Rift. And we also know from trace elements that for melt heterogeneity to be preserved, we must have discrete sills at these pressures. And this all provides new petrological evidence for this focused mid-crustal magmatic intrusion in the rift. Thanks very much for listening to me, and do feel free to get in touch using my email address or drop me a follow on Twitter. Thank you very much.